This particular lecture is all about Lyapunov theory again, and then the outline of this particular lecture is like this. First, we will go through this review of Lyapunov theorems. Then it is we will see the whatever we discussed towards the end of last class. This is Lassalle's theorem and all, and then we will try to use this Lassalle's theorem to something to estimate something called domain of attraction, and any asymptotically stable equilibrium point obviously has a neighborhood about which it can attract trajectories, and that particular domain is called the domain of attraction. It is in general not easy to estimate, but once you estimate there are a lot of potential uses actually. In other words, you can think of like stopping your control action once the trajectory enters this domain of attraction. Okay, that is one of the uses that you can think about actually. Okay. So, anyway, so let us proceed with that quick review of Lyapunov theorems and some concepts that we discussed last previous two classes and all. So, first what we discussed is the system dynamics is in homogeneous form, okay, and this is also like autonomous forms. In other words, explicitly time does not appear in function as well as control also does not appear in function. However, if the control is in a state feedback form, then this homogeneous form also applies for closed loop system dynamics actually. Okay. Then we are interested in this open and connected subset of Rn, and the function is defined from D to Rn actually, and we are interested in analyzing the equilibrium point, stability behavior around equilibrium point primarily. So, equilibrium point is defined as some the state derivatives are equal to 0. So, whatever solution pops of these are equilibrium points. About each equilibrium point we wanted to analyze the stability behavior. There are a bunch of definitions that we studied, and this first thing is what is called a stable equilibrium. In other words, if you start with some finite ball, then for all time your trajectory remains in another finite ball, and the radius of these balls can be functions of each other also actually in general. So, that is the kind of weakest notion of stability, and if it does not satisfy that also, then it is unstable actually. Okay. But if it satisfies the weakest notion, then we are further interested, and for that we need this idea of convergent equilibrium. That means, eventually if the trajectory goes to the equilibrium point, no matter where it travels on the way, then it is convergent equilibrium. And obviously, if if an equilibrium point satisfies both stability and convergent behavior, then we tell okay, it is asymptotically stable equilibrium, which is always desirable to have actually. Okay. Then is even further stronger notion of stability, which is exponential stability. So, the trajectory not only goes to the equilibrium point, but the rate of decay is also exponential. Okay. This is the strongest notion and all that. And for every practical purpose, we tell okay, we can always do change of coordinates and all that. So, we take this equilibrium point to be the origin actually. Then with that we had some bunch of theorems, Lyapunov theorems and all, Lyapunov stability theorems and all. The first theorem told that okay, if this x equal to 0 is an equilibrium point of this system, provided this V is a continuously differentiable function such that these things happen. But if it is a continuously differentiable function, and in addition to that point number 1 and 2 are also satisfied, then it is also something called a positive definite function. So, we start with a positive definite function, and also want to make sure that the rate of change of that positive definite function is less than equal to 0. It is a negative semi definite function, and if that happens, then x equal to 0 is stable in the weakest notion actually. Okay. Now, obviously, weakest notion is something that we typically do not like so much. We want to conclude further, and for that we have this asymptotically stable equilibrium condition sort of thing. And that is for that the only change is if you mark here this inequality becomes this strictly strictly less than 0. Okay, all other things will remain exactly same. So, but the V dot needs to be negative definite function. Okay. And that is, as we discussed, is an order of magnitude complexity, higher in complexity, because to conclude negative definiteness, V dot needs to be a function of all components of state variable. If it is one component is left out, then also we cannot conclude that, we can conclude only semi definiteness actually. So, that is the difficulty what he throws up actually. Anyway, so the theorem 3 in this regard is like how do you call that, I mean these things only guarantees you some sort of locally asymptotical stable behavior. That means around the neighborhood of the equilibrium point, then only, I mean you can conclude something. But how about global behavior? And if you want global behavior, then in addition to all those conditions, we have one more condition, which is the V of x, the Lyapunov function, needs to be radially unbounded as well actually. Okay, that is as x goes on further and further away from origin in whatever all directions, V of x has to keep on increasing actually. Okay. Now, that is V of x needs to be radially unbounded, then only you can talk about like global asymptotically stable behavior actually. Okay. All right. Then exponential stability conditions, in addition to all the conditions that we discussed about asymptotic stability, we need to have this further equations, I mean inequalities needs to be true, that V of x needs to be bounded by exponential functions both below and above. Okay. And then V dot also needs to be bounded above by this negative k3 times norm of x whole power p actually. Okay. So, V of x needs to be bounded from both sides with exponential functions, and V dot needs to be bounded above by this negative constant sort of thing. Okay. So, remember this itself is a negative number what you have in the right hand side. So, if these two conditions are satisfied in addition to whatever conditions you talk here, okay, then it is locally that exponentially stable, or if it also satisfy these conditions where V of x is radially unbounded, then it will become globally exponentially stable. Okay. So, but as we discussed also previously, these conditions are not in general for nonlinear system, these conditions are difficult to utilize also. Okay. But for linear systems it is possible by using this Rayleigh inequality and all that actually that we discussed before. All right. Now, coming to this linear time invariant system, there is a special class of system, we also discussed about that, and to analyze the stability behavior of that particular class of systems, we took a Lyapunov function candidate like that, where P is a positive definite matrix, and then we saw that V dot is nothing but if you start with that and then apply this derivative rules and all that, then x dot you substitute with a x and x dot transpose is x transpose a transpose like that, then it throws something like that. So, if you have to have this V dot strictly negative definite, then we can aim that okay, V dot needs to be something of this form, where Q is a positive definite matrix. If it happens, then these two equations whatever we have as V dot here and whatever you have as V dot here needs to be equal, and if that happens for non-trivial x solution and all, we have to have this Lyapunov equation satisfied. And this Lyapunov equation being a linear equation, it is a function of P and Q, where P and Q both need to be positive definite matrix. So, one way of looking at that is I will probably select P and then solve then evaluate Q, but that does not help us too much, because the solution can be like I mean the conclusion can need not be one shot actually. So, but you really want to have one shot solution, I mean check and all that, then we start with Q positive definite any Q and then solve for P actually. And if it P happens to be also positive definite, then we are done, and if it does not happen to be positive definite, then also we are done actually. Okay. And this is primarily because we are talking about linear systems actually. Anyway, so that is the procedure. So, you can choose an arbitrary symmetric positive definite matrix Q, and if I can select any matrix, then probably I will go ahead and select I identity, and then we solve for P matrix from Lyapunov equation here. Okay. And then we tell okay, whether you check whether this P whatever solution pops up, okay, we just check one time whether P is positive definite or not. And if P is positive definite, obviously I mean both V and V dot P is positive definite, then V of x is positive definite, Q is also positive definite, since V dot is negative definite. So, that is how all these things are satisfied, and you have this this clear cut result whether the equilibrium point is asymptotically stable or not. That is the way to utilize this Lyapunov theory for analyzing linear system equations, I mean linear system dynamics. And there is a great theorem which is like Lyapunov's indirect theorem, also we discussed about that. So, what it tells is okay, around the equilibrium point you linearize the system dynamics and study the behavior of the linear system dynamics, and that can be rather easily studied from eigenvalues and all that. And if all the eigenvalues of this matrix A are in the left hand side of the complex plane, then obviously we know that the linearized system is exponentially stable. But using this conclusion, it also turns out that the nonlinear system is also locally exponentially stable. Okay. That means, that the region may be small, but still the guarantee is there that if the linearized system is stable, then the nonlinear system is also stable. Okay. So, that is the beauty of this indirect theorem, and if you, and it is very direct straightforward approach to test whether the system is actually locally I mean kind of exponentially stable or not. If you really want to have that kind of very quick conclusion, all that we need to do is linearize the system dynamics and then study the behavior of the eigenvalues of the matrix actually. Okay. Then on the way we discussed about instability theorem also, because this all these Lyapunov theorems happens to be this sufficiency conditions and all. So, we are never sure what we are, I mean whether if one selection fails, then we are never sure whether some other selection will succeed or not. So, because of those difficulties and all, there are also like people have thought about instability theorems, in the sense that if the system is really unstable, no matter how whatever attempt you do for selecting a good Lyapunov function, you will never succeed actually. So, because of that there are theorems that we discussed about that, and then essentially it tells you that if I select a v of x which is positive definite and v dot happens to be also positive definite, then I am done. But you do not need those strong conditions, you can simply need like one point x 0 close to this origin, so that v of x is positive and v dot also needs to be positive in this particular set actually. Okay. So, this is what we discussed before actually. Okay. So, this is one of the instability theorems. There are many other instability theorems as well actually. So, if somebody can show this system dynamics is really unstable using one of the theorems, then also you are done actually. And also remember, instability theorems are also sufficiency conditions only basically. Okay. And we also discussed last class about some construction of Lyapunov functions ideas, because standard Lyapunov functions, you know, this quadratic functions that x transpose x or x transpose p times x, where p is positive definite. That is a very standard way of starting a guess basically. If it does not happen, then you can probably, other alternative idea is to select a total energy, that kinetic energy plus potential energy, but other than these two we are kind of blind of what to take actually. So, because of that we studied about some ideas of constructions of Lyapunov functions, and one of the idea happens to be variable gradient method, where you do not select the v, but we want to select a gradient vector del v by del x actually. Okay. And once you select a gradient vector del v by del x, we will be able to solve for v from that expression actually, and integrating one direction, one component direction at a time sort of thing actually. Okay. But the point here is this g of x must satisfy some sort of a curl condition. That means, if I take del g by del x, that matrix needs to be symmetric actually. Okay. All right. So, the integration can be done component by component, that is what we discussed before. Once you know that g 1, g 2 or g n are selected already, then v of x you can compute it that way actually. So, you can start with some sort of a pre parameters and all that, and then those pre parameters can be adjusted to see that okay, g of x needs to be positive, this del g by del x needs to be symmetric actually. So, using that you can satisfy some of those things. We have seen many examples on the way also. If you review this previous two lectures and all, many examples were there to clarify some of these ideas actually. So, this is the condition that I was talking. The only restriction that we are placed here, I mean we have to work with that, is del g by del x matrix needs to be symmetric actually. So, with that selection we will be able to solve for v of x, and then you proceed with your selection of that, with your evaluation of v dot and things like that actually. All right. So, then we also studied something like Krakowski's method and all that, where there are one version of the theorem is very straightforward. All that it tells you is okay, given the system dynamics, you formulate this A of x. Okay, this is not linearization, it is simply computing the Jacobian matrix in a symbolic form. And once you compute that, then A plus I transpose you select, there is another matrix big F of x, and then tell okay, this equilibrium point is locally asymptotically stable if this big f of x is negative definite actually. Okay. And the corresponding Lyapunov function by construction will be f transpose f rather. Okay. So, that is very easy to see. Okay. And in addition to that, if this happens to be radially unbounded, of course, this f transpose f we do not have direct control on that, because f is a system dynamics actually. But if it happens to be radially unbounded, then it is also globally asymptotically stable. but see this I mean realizing this one is I mean feeling this one, this intuitive feeling is not very difficult, because if you see V of x is that, the f transpose f, then V dot is nothing but that, and then f dot is nothing but del f by del x transpose x and x dot and all that. Substitute both them, I mean all the expressions there, and then you tell okay, if the V dot is nothing but f transpose big F times small f. So, if this happens, then obviously very clear that f of x has to be negative definite for V dot needs to, I mean for V dot to be negative definite. Alright. So, what it tells you is, you given a system dynamics, you just try out with this simply evaluating A and then f, which is A plus A transpose, and then make sure that this big f of x matrix rather is negative definite matrix. I have seen some example also actually. Then there are generalized Krakowski's theorem also we discussed. Okay, this restriction turns out to be too much here, because we are all dealing with the system dynamics that is given to us. We do not have any direct control on the system dynamics here, right. I mean system dynamics is something and the V of x turns out to be f transpose f. So, there is no freedom actually, and if it happens that f of x happens to be negative definite, we are lucky, otherwise not actually. That means the restriction or conditions placed on this is relatively higher side. So, we wanted to kind of relax those and all that. So, that way it leads to this Krakowski's generalized theorem, which tells you that you still evaluate this A of x similar way, so rather same way. Okay. Then you construct f of x not just I mean that otherwise this A plus A transpose sort of thing, but you construct it something like A transpose P plus P A plus Q with two positive PDF matrices also you have to select on along the way actually. You select P and Q, two positive semi definite matrices, and then constructs this f of x, and then you make sure that f of x is not really negative definite, but it is negative semi definite. Okay. So, not only it gives you a freedom of selecting P and Q, and hence it gives you a lot of freedom of constructing this f of x, but also tells you that f of x needs to be only positive semi definite, sorry negative semi definite. So, that way negative definite to negative semi definite is a lot of relaxation of condition. In addition to that, it gives us freedom of selecting P and Q. Okay. So, that way it turns out to be much more general and convenient to use actually. Okay. And again, if this f transpose P times f of x is radially unbounded, obviously the results are global actually. Okay. And that is also not that difficult to solve. I mean, you can start with same V of x, then evaluate this V dot, which is f transpose P f dot plus f dot transpose P f and all that. Then f dot you substitute again similar way, and then here is the trick, you do something like plus minus q actually. Once you have that, then this turns out to be like this minus that, and because q is a negative definite matrix, then f transpose q f is already negative definite. So, all that we need to make sure is this fellow, I mean this part of the equation needs to be negative semi definite. Okay. So, that is how it gives us much more flexibility sort of thing. So, this is like two methods, one is variable gradient method, another is Krakowski's theorem and all that. Then we also discuss something called invariant set, limit sets and all that, and what is that? The invariant set turns out to be like if my initial condition is within the set, then for all time my trajectory will remain within the set actually. Okay. So, obviously, then the set is something like invariant set, and an equilibrium point obviously is an invariant set, trajectory of an autonomous system is an invariant set, many other examples we gave actually. Limit cycle is an invariant set like that. Okay. Now, limit set I mean this is the set whatever except t tends to in the limit actually, starts with something, but as t goes to infinity, then it will go to I mean all trajectories will go to that particular set actually. Okay. So, that is that particular thing is called limit set actually. Okay. So, I mean example sense, asymptotically stable equilibrium point is a limit set for any solution starting from a closed neighborhood of the equilibrium point. If it starts with a closed neighborhood, obviously the trajectory is going to go to the equilibrium point. So, obviously that becomes a limit set actually. As t goes to infinity, under the limit this except t will go to that particular set. Okay. And stable limit cycle is the limit set of any solution starting sufficiently close to it actually. Okay. So, that is a definition sort of thing. Then we also studied some sort of Lassalle's theorem, that is what we ultimately led towards, And before studying the Russell's theorem in full, we actually studied a subset of this theorem, which told us that okay, even if B dot happens to be negative semi definite in a bounded region R, okay, of course, the region needs to be bounded actually, which needs to be a subset of D also, and then V dot equal to 0 happens only at the equilibrium point, okay, nowhere else on that particular region R. Then what I mean, what it means is B dot of x does not vanish along any other trajectory in R other than the null solution x equal to 0, right. So, then it can still conclude that x equal to, I mean that origin x equal to 0 is globally asymptotically stable actually, okay, provided V of x is radially unbounded. If not radially unbounded, then you can always tell it is stable or locally asymptotically stable basically, okay. So, what is the utility sense, we solved 2 examples and all, and one example, I mean this theorem is actually very neat, because most of the time what happens again is we will be able to solve V dot of x is negative semi definite rather easily, but showing negative definiteness is difficult, but using this particular idea of Lassalle's theorem makes our life much easier actually. Okay, so that is what we saw one or two examples. One example was like that. We started with this second order system and all that, and then we chose this V of x to be like this, where alpha is positive. So, again this V of x is certainly positive definite. Then V dot happens to be like that, del V by del x transpose times f of x. So, del V by del x, if we evaluate, this is 2 alpha times x 1 from here and 2 x 2 from here, and then f of x is like this x 2 and then all that. So, we put it there. Then evaluate this expression actually, okay. Then you tell V dot of x, I can rearrange it to be in this form, and it certainly happens to be negative semi definite actually, okay. Now, if it is negative semi definite, we are stuck because we can only conclude stability in the weakest notion, but we need to continue further. So, we told okay, let us analyze the situation V dot of x equal to 0 for all time. Let us see where it happens actually, and if it happens only at the origin or equilibrium point, we are done actually in a way. Okay. So, and that actually led us to the conclusion that V dot of x equal to 0 happens only at x 2 equal to 0, and if x 2 happens to be 0 for all time, then x 2 dot is also 0, and x 2 dot happens to be like this. Okay. So, that substituting that one, and then also noting that x 2 is already 0, I mean that is anyway 0. So, you are left out with because x 2 is 0 means this one is cancelled out, this one is cancelled out anyway. So, you are left out with no choice other than x 1 equal to 0. So, it happens that x 1 and x 2 both equal to 0 whenever this V dot is equal to 0. Okay. So, V dot equal to 0 happens only on the equilibrium point, and hence using this theorem we tell okay, V dot, I mean this even if V dot is negative semi definite, the origin is still asymptotically stable. Okay. So, that is that is what we are able to solve. Okay. So, that is what it is written here, but in addition to that you can also see that the choice of the selection of V is actually radially unbounded. It is a quadratic function after all. For any positive alpha, it is radially unbounded, because the moment this quantity keeps on increasing, V of x also keeps on increasing anyway actually. Okay. So, if that is true, then obviously the result is global. That means the origin is globally asymptotically stable basically. Okay. Then we towards the end of last lecture we talked about this Lassalle's theorem sort of thing. In that is a theorem that Lassalle gave, a slightly bigger theorem than what we just saw as a subset sort of thing. And this theorem tells that this V defined between this domain D to R needs to be a continuously differentiable function. Again, it need not necessarily be a positive definite function actually. It is simply necessary that it needs to be continuously differentiable, that is all. And then this following conditions hold good actually. Okay. What are those conditions? First condition is there is a set M which is a subset of D is a compact set. Compact is something like closed and bounded set. Okay. And not only it is a compact set, but this particular subset M is invariant set with respect to the solution. Okay. Once the solution enters to this M, it cannot leave actually. Okay. And within that M, it is also true that V dot is less than equal to 0. Okay. And then we define that set E, okay, a subset of that particular M rather, okay, what it tells you is okay, let me select only that particular set for which B dot is equal to 0. M can contain everything for which B dot is less than equal to 0, but I will select that particular set E which is actually V dot of x is equal to 0. Okay. And then I will select the largest invariant set of this particular set E. Okay. Because E can have multiple solutions sort of thing, like for example, I will also take you through an example where it gives you E is a union of two sets, the two subsets where equilibrium point as well as limit cycle actually. So, then you have to select one that particular subset which is the largest invariant set in that particular E actually. So, if you satisfy all these conditions 1, 2, 3, 4, then the conclusion is every solution which starts with this M, okay, will ultimately approach N as t goes to infinity, and it is very easy to see the previous theorem that we discussed here. Okay. It will satisfy all those conditions actually. Okay. So, we will see that. Okay. So, essentially what it tells you that I start with some set M for which I am already on the solution trajectory basically. Okay. That is what it tells actually. Okay. Is invariant with respect to the solution set actually. Then in that M it also turns out that V dot is less than equal to 0. Then I define V which is equal to 0, less than I will throw out, and then I will tell N is the largest invariant set in E. Okay. So, then it tells you that okay, if I start with M then I will approach N ultimately. Okay. So, let us see that one example sort of thing, and then ideas will be slightly more clear. But before that there are a couple of remarks here, and first thing is I told already V of x requires only to be continuously differentiable function, it need not be a positive definite function. Okay. And as we also discussed, Lasser's theorem applies not only to equilibrium points, it also is more general analysis tool, and we will see one example which will be able to talk stability behavior of limit cycles also. Okay. Then we all know that the earlier theorem that we discussed, okay, that was that is obviously some sort of a subset of this theorem. In other words, it can be derived as a corollary of this theorem actually. Okay. All right. Let us see that example, and then ideas will be probably more clear. So, let us talk about an example where x 1 dot is given like this and x 2 dot is given like that, where beta is greater than 0. Okay. And if it is like that, suppose I put x 1 dot equal to 0, x 2 dot equal to 0, okay, then let us say beta is strictly greater than 0, okay, that way. Then what happens actually? Okay. X 1 dot one solution ultimately is x 1 and x 2 both equal to 0. If x 1 and x 2 both equal to 0, both are 0 anyway. Okay. But there is interesting thing, I mean that is the only equilibrium point sort of thing actually. Okay. As far as equilibrium point is concerned, we have only origin as the equilibrium point. I mean no question about that, because it does not throw any multiple solutions out of that actually. However, you can also analyze, let us analyze this expression with respect to the system dynamics. This is the same expression what you have here with a negative sign probably. Okay. So, if you take dy dt of this expression x 1 square plus x 2 square minus beta square, where beta is a constant anyway, then it turns out it is 2 x 1 times x 1 dot plus 2 x 2 times x 2 dot, this is 0 anyway. So, then x 1 dot you substitute this, and x 2 dot you substitute that expression here. Okay. Then carry out the algebra, and it will turn out that I can nicely combine this dy dt of this expression as something like 2 times this one x 1 square plus x 2 square into that again. So, this expression what you are talking about is 0, okay, as soon as this happens. Okay. This will never be 0 other than equilibrium point, so forget about it. But other than equilibrium point, this can happen actually obviously, and if it happens, then this expression whatever you are analyzing dy dt of this expression happens to be 0. That means what actually this particular expression, okay, what you are talking, if I satisfy this equation in the beginning itself, then I will keep on satisfying this equation, because it is the derivative rate of change of rate of change of this expression is 0. Okay. The condition is this again this expression, right, x 1 square plus x 2 square minus beta square. If I take x 1 square plus x 2 square minus beta square equal to 0, then the rate of change of derivative of that particular expression is again 0. Okay. So, that tells us that we have got some sort of a limit cycle actually. If I start with any point on this particular trajectory which satisfies this equation, then I will continue to stay with that particular trajectory, I mean that particular locus only basically, okay, this x 1 square plus x 2 square minus beta square. That expression will remain constant, it will never change actually. But x 1 and x 2 can keep on changing, because x 1 dot x 2 dot is not 0, x 1 dot x 2 dot is still some value, and that value is okay. If you go back to and see that only this portion is becoming 0. So, you still have x 1 dot is x 2 and x 2 dot is minus x 1. So, that means these variables they change, but they change in such a way that this expression remains constant actually, and that actually gives us some sort of a limit cycle behavior. If I plot that in phase plane x 1 and x 2 there, then x 1 x 2 are changing, but the constant, I mean the way they change, the way they interact with each other is that this expression remains constant actually. And as long as I satisfy this x 1 square plus x 2 square equal to beta square, that is my expression. That means x 1 will change like x 1 dot is x 2, x 2 dot is minus x 1. What does that tell you? Let us say if I am in the positive quadrant, then x 1 dot will change positive, x 1 will keep on increasing, but if I have x 2 negative, okay, which happens in third and second, I mean fourth quadrant, x 2 negative, then x 1 dot will be decreasing. So, in the third and fourth quadrant x 1 will start decreasing, okay. Decreasing means x 1 value will keep on becoming lesser and lesser basically, and that, and then in the first two quadrant, okay, it will keep on more and more actually, x 1 will keep on increasing. So, obviously, we also have one more conclusion here, that not only you have a limit cycle, but the limit cycle rotates in a clockwise direction basically. So, these are like further analysis and things like that actually. Okay. Now, we will go back to this Lyapunov function and try to kind of see what is going on there actually. So, this Lyapunov function that we started with, I mean this so far we have not started with any Lyapunov function by the way, we just simply analyze this expression and all. And now, let us start with an Lyapunov function, I will take the same expression with a whole square term actually. Okay. So, obviously, this happens to be positive semi definite in R square. Okay. Now, that is okay, because the Lassalle's theorem does not demand that v of x is positive definite, it just needs to be continuously differentiable. So, do not I mean even though we can call that as Lyapunov function something like that, it is really not a Lyapunov function candidate, it is just a function candidate for which we want to apply Lassalle's theorem actually. Now, let us say we analyze this b dot of x, okay. Okay. And well, I mean having said that, what it turns out that it is convenient to work with Lyapunov functions also. Okay. So, you can this particular example you can think of that as a Lyapunov function candidate around the local neighborhood of the limit cycle. Okay. If I, because this particular expression, if it is non-zero, it gives us some sort of a distance measure from the limit cycle. Okay. If it is 0, we are moving on the limit cycle. If it is non-zero, we are moving away either inwards or outwards, either way. So, this actually gives us some sort of a distance measure quantity basically. So, if I take this particular function, it is not only continuously differentiable, but it is also some sort of a greater than equal to 0 as long as we are not on the limit cycle. I mean that is the only condition actually. Okay. Okay, probably you can, if you want to be more precise, then b of x is greater than equal to 0 other than okay, you can complete this statement other than the limit cycle. Okay. Now, what I mean is b of x is strictly greater than 0 as long as it is not on the limit cycle. If it is on the limit cycle, it is still equal to 0, which is still true actually. So, that the statement is not wrong in general. Okay. V of x is greater than equal to 0, that is true actually. But as long as you are not on the limit cycle, any other direction you are going, then V of x is positive actually. Okay. So, then talk about V dot happens to be del V by del x x1 del V by del x2 row vector, these are column vectors. So, do the regular algebra whatever you are having, and remember del V by del x1 is del V by del this expression, whatever expression, into this expression del by del x1 of this expression again inside. So, that means 1, 2 and 4 will cancel to be half, and then when you take 2 times x1, that 2 will also go. So, you will be left out with this expression actually into x1 of course, the first quantity, and this expression is this one into x2, okay, and then these two expressions are there. So, you try to put them all together. Remember, this is a scalar quantity, this is a row vector and this is a column vector. So, it is 1 by 1 and then this is 1 by 2 and this is 2 by 1. So, ultimately you are working with a scalar quantity. So, if you carry out this algebra, okay, and then try to simplify and all, it turns out to be like that. Okay. So, it happens to be like that, then because here this is actually nothing but some sort of a 4 V x actually, this expression what you see here. Okay. Okay, this particular expression what you see here, if you compare to that one, okay, this is nothing but 4 V of x really, 1/4 in 4 will go actually. So, what you are telling, because this particular quantity is anyway greater than equal to 0, okay, always, okay, and this quantity also is greater than equal to 0 always. So, obviously, you are with a negative sign of course. So, we will end up with a case where V dot is actually negative semi definite basically. Okay. Okay. And this is also like a side comment that V dot is nothing but minus 4 times this expression times V of x actually. Okay. That is some further connotations and meaning which will not discuss here anyway. Okay. Anyway, so V dot happens to be negative definite, I mean negative semi definite basically. So, now we will study when this V dot happens to be equal to 0. Okay. Now, if V dot is equal to 0, remember V dot is this expression anyway. Okay. So, this V dot happens to be 0, either I mean x 1 square plus x 2 square equal to 0 or x 1 square plus x 2 square equal to beta square. I mean this expression clearly tells us that. So, if it happens to be equal to 0, then we will end up with origin. I mean x 1 square plus x 2 square equal to 0 will happen only when x 1 x 2 both happens to be 0. So, that means this condition will give us an origin is the thing, that means equilibrium point, and this particular condition will give us a circle which is nothing but limit cycle actually, okay, limit cycle of radius beta basically. All right. Now, it is we are kind of ready to see this meaning of this Lassalle's theorem conditions and all that actually. So, first thing first we define say invariant set some sort of M. So, go back to that and then tell sorry, we define a compact set M, okay, which is invariant with respect to the solution basically. So, this is obviously if you define M, okay, with some sort of a V of x is less than equal to C, then this particular set, I mean we did not talk about whether it is invariant or not yet, but let us define it this way, and it again tells us that by construction this M is certainly closed and bounded. Okay. Why it is bounded? Because it is an inequality sign anyway. Okay. So, everything it is like bounded below V of x happens to be a positive function anyways, and then that is less than equal certain quantity. So, that is bounded. Why it is closed? Because it is a regular expression, okay, first of all it is a continuously differentiable expression with this I mean this equality also taken into account. So, boundary values are also included basically. Okay. So, M happens to be like closed and bounded, and hence it is a compact set. That is the first thing that we need to worry about. The M has to be defined in such a way that it is closed and bounded. So, it has to be compact set actually. Okay. Then we have to see whether it is invariant with respect to solution or not actually. So, now we go back and see I mean this particular thing what you have defined, okay, within this set, if we start with the solution, I mean if you start with the solution of the system, then obviously it will remain there only, because V dot happens to be negative semi definite anyway. V dot V is whatever V dot is happens to be always less than equal to 0. So, if V is bounded above, okay, then the solution will always satisfy this actually. So, that means it is invariant with that. Then we have to find a set E, okay, for which V dot is equal to 0, and V dot is equal to 0 happens either on the equilibrium point or on the limit cycle. So, if I take union of these two, then obviously it tells okay, this E is nothing but the union of those two actually. Okay. Then we have to find the largest invariant set of that, okay, and obviously the largest invariant set is certainly E itself, okay, because in this set this if your trajectory starts with equilibrium point, it stays on the equilibrium point. If it starts with an limit cycle, it stays on the limit cycle also basically, and the union of that is actually largest set actually. Okay. No other possibility does arise. One possibility is starting with the equilibrium point, one other possibility is starting on the limit cycle. Okay. And if I take union of that set, then obviously that is the largest one possible actually. Okay. So, N whatever we are talking is nothing but equal to E. Okay. So, Lassalle's theorem if you apply now, what it tells you is every solution that starts with this set M will ultimately converge to this set N basically. Okay. That means either it will converge to the limit cycle or it will converge to the equilibrium point, that is all it tells you. Okay. Now, let us do some little bit further analysis. So, we want to wind up this idea of whether it is either or and things like that, we do not want that actually. Okay. Now, further analysis we assume, I mean we know that this particular function that we selected is a measure of distance, of point x1 x2 to the limit cycle basically, right. Hence, v of x is 0 provided this condition holds good actually. Okay. Right, and if x1 and x2 is equal to 0, then v of x takes this value. Okay. So, if I just pictorially draw a little bit, then what happens here is x1 x2 is there somewhere, and on the limit cycle Lyapunov function is 0, and as I go along more and radially inward or outward, it keeps on increasing, and if I am on the equilibrium point, this v of x that I have selected, okay, takes this value of beta 4th by 4 actually. On this beta 4th by 4 is on the origin basically. Okay. So, let me select a beta such which satisfies this condition. Okay. This beta is less than beta 4th by 4 sort of thing. That means, I limit my beta to be in this like if I have meaning, then beta has to be greater than that value and all that. Then I define a C which is in between these values and all that. Okay. Then I tell okay, if I apply this Lassalle's theorem and all that, then ultimately it tells me that it will all trajectories that start with m will eventually converge to n, right. That is the meaning of this. So, if I define a cycle like that, why I am doing all that? Because I am excluding the origin actually. If I exclude the origin anywhere else I start with, then my v of x happens to that largest invariant set contains only the limit cycle. Okay, because I am not considering a region to begin with where an origin is also included, I am excluding that. So, if I exclude that, then everything will go to the equilibrium point actually. Okay. Now, it also tells us that if I like just epsilon which is just slightly close to 0, that means I am almost touching equilibrium point, but I am away from that, then also I will go to the equilibrium, I will go to the limit cycle only. If I start anywhere very close to the okay. If I start wherever, I start very close to that, ultimately I will go and converge to the limit cycle actually. Okay. Okay. And not only this side, I can start with that side also, and then ultimately I will converge that. Okay. So, both sides there is a finite domain for which I can think that the limit cycle is attractive actually. In other words, we have already proved using Lassalle's theorem that the limit cycle is this asymptotically stable actually. Okay. And also as a corollary, if I start very close to equilibrium point, then also I am going towards the limit cycle actually. So, what it tells us that the origin happens to be unstable actually. Okay. Origin that also can be proved using this instability theorems and other things what we have discussed before, but as a corollary of this particular analysis, it also tells that not only the limit cycle is stable, but the equilibrium point is unstable as well actually, both. So, that is the thing of that is the beauty of using Lassalle's theorem. So, if you see example, but most of the time we use the corollary version of that, the small version of that, the smaller version, where you tell equilibrium point is asymptotically stable or not. But the Lassalle's theorem itself, if you want to apply in a generic way, it can be like you can derive further conclusions, and it is more general actually. Alright. So, before ending of this discussion of Lyapunov theorems and all that, and also remember all the thing that we are discussing in this particular course here is Lyapunov theorems as applied to autonomous systems. In this now if you have this x dot equal to f of tx, tx sort of thing actually. Okay. So, then it is a different ball game altogether basically. We have to talk about slightly different notations and all that, where things can be different actually. Okay. So, there we have to talk about uniform stability and things like that. So, we are not able to discuss that because those are advanced concepts and we probably do not need that also. Most of the applications we are okay with x dot is f of x, not necessarily x dot is f of tx basically. Alright. So, last topic is domain of attraction. This as we discussed in the beginning of this lecture, every asymptotic stable equilibrium point by definition is attractive. That means, if I start to sufficiently close to that equilibrium point, because the equilibrium point is stable, by definition it will attract the trajectories towards that. So, obviously, there is a domain of attraction around that, right. So, now the question is, can we define it properly, and if possible can we estimate that properly. Okay. So, the domain of attraction definition is like this. So, let psi of x t be trajectories of x of x dot is f of x with initial condition x at t equal to 0. Remember, we are not talking about a particular x 0, we are talking about that x 0 itself can be varied. Okay. So, that we will get a number of trajectories with different x 0s and all that actually. Okay. So, if you have this particular thing, then that particular set of trajectories I am defining as psi. Okay. Then the domain of attraction is defined as x belongs to D such that the psi of x t goes to x e, because all such trajectories that I start with the different initial conditions and all that, everything will go to 0, I mean go to this equilibrium condition, equilibrium point, okay, as t goes to infinity. Then this d of a that I am defining as subset of this d turns out to be the domain of attraction actually. Okay. Remember, x dot is f of x is valid in a domain D, and this dA is a subset of that domain, for which every trajectory that starts with this dA will ultimately go to the equilibrium point. I mean, that is very intuitively what we discuss actually here. So, the philosophy, as I told, around any asymptotically stable equilibrium point there is a domain of attraction, and the question obviously is, can we estimate this domain of attraction? Very fortunately, answer turns out to be yes, but also unfortunately the answer turns out to be very conservative. Okay. That means, the domain of attraction can be larger, but you may not be able to estimate that larger bound. You will be able to use it as you will have to be happy with a smaller bound estimate and all that, and largely because these Lyapunov theorems are sufficiency condition again. Okay. Anyway, so let us go through a example and try to get our ideas slightly clear here. So, let us talk about again a second order system, x 1 dot is 3 x 2 and x 2 dot is like that, minus 5 x 1 plus x 1 cube minus 2 x 2. So, equilibrium point again I put them to be 0, x 1 dot x 2 dot is 0. So, obviously, x 2 is 0. Okay. Once x 2 is 0, x 1 I am left out with this 5 minus 5 x 1 plus x 1 cube equal to 0. That means, x 1 is either 0 or plus or minus root 5. So, the choices that I have here is either equilibrium, I mean either origin, or plus root 5 by plus root 5 and 0, or minus root 5 by and 0. So, we will not worry so much on these two, let us say, but we will worry about this particular thing. Okay. Let us study the stability behavior around origin. Okay. Then start with some Lyapunov function candidate and all that. Okay. And this Lyapunov function candidate with respect to that, let me analyze V dot actually. So, V dot happens to be like again del V by del x, del V by del x 2 and all that, you put f 1 f 2 and then analyze this term. And okay, for conveniently, because there are several free parameters here that we need to select, we need to select it in such a way that let us say these coefficients which are odd coefficients for us to analyze, they are 0 basically. So, I will select this one to be 0, that one to be 0. So, I really do not have to bother about this particular x 1 q x 2, x 1 x 2 all that actually, these are odd terms to handle really. So, we will be left out with only even powers of x 1 or x 2. Okay. So, once you do that, okay, these two conditions again are I mean actually a, b, c, d 4 variables and 2 equations. Obviously, it is another constant thing, we have infinite solutions. So, one solution we will select it that way, okay, so that we can work further actually. So, then it turns out that v of x turns out to be like that with that particular selection. Remember, a is 12, b is 1 and all that in this expression. Okay. So, if you substitute there, then v of x turns out to be like that and v dot turns out to be like that. And if you analyze little bit carefully, then remember x 1 fourth is less powerful when x 1 goes to 0, close to 0. So, this one will not be very, this negative x 1 fourth will not be very punishing actually. Okay. So, obviously, it tells us that it is locally PDF function, okay, this particular thing, and then v dot whatever is this here. Okay. Remember this there is a minus 30 x 1 square, but plus 6 x 1 fourth, which again this is less powerful. So, it will tell okay, it is locally negative definite. Okay. So, this is locally PDF and this is locally NDF, so and hence the origin is locally asymptotically stable. Okay. Now, the question begins that okay, let us analyze little further and tell okay, when this condition is universally true, let us say. So, V of x is greater than 0 and V dot is less than 0 as long as this x 1 satisfies this condition. Remember, it is because the trouble making things are x 1 only. X 1 is everything is positive here, only minus x 1 fourth, everything is negative here plus 1 x 1 for 6 x 1 4. So, the trouble making values are only x 1 terms actually. So, now we want to analyze the condition based on x 1 bound, let us say, and it turns out that as long as x 1 is bounded like that, bounded below and above with minus 1.6 and plus 1.6, then V dot is guaranteed to be less than equal, I mean strictly less than 0. Okay, that means V dot is negative definite. So, we may be tempted to conclude that if I define a region D, which is like x 1 is bounded like that, that means I define a region something like this. Okay, this is like say x 1 and x 2. So, x 1 is bounded between that. So, it is 1.6 here and minus 1.6 here as in okay. Well, always a problem. Okay. Okay, minus 1.6 here. So, it tells you okay, I will define this region. Okay, this region appears to me that okay, in this particular region infinite stripe really it that V dot is negative actually. So, we are very kind of tempted to conclude that in this region my V dot is because my V dot is negative all the time, this is my domain of attraction. Okay, but the conclusion turns out to be incorrect, and the correct thing we will see actually. Why is it incorrect? Because if this domain D what you have discussed, I mean what you have defined here, this infinite stripe, it is not an invariant set actually. Okay, that means if you start with any solution here, I mean any point here, you may not remain within that point, I mean this region actually, the trajectory may go away from that region. And because there are kind of we will see that there are kind of local minimums and things like that there actually. Okay. All right, we will see that. Okay. So, theorem domain of attraction tells you that okay, the x e needs to be an equilibrium point first of all of this one, and V of x d to r needs to be a continuously differentiable function. Then M needs to be a compact set containing x e such that M is invariant with respect to the solution. All these are incompatible with Lassalle's theorem by the way. Okay, and V dot is such that V dot is strictly less than 0 for every point other than equilibrium, but on equilibrium V dot is equal to 0. Okay. So, these are like important thing actually. V dot is equal to 0 only on equilibrium point, V dot is always otherwise it is less than 0. Okay. And this M that we are talking about is a subset of this D domain, the compact set containing x e equilibrium point, such that M is an invariant set with respect to the solution of the system. Okay, that has to be guaranteed sort of thing actually. And under these assumptions, M is the subset of M, whatever you are talking about is not the domain of attraction, but M happens to be a subset of the domain of attraction. That means, you can that is the thing that I was talking about, that our estimate can be very conservative. Okay, what you will be able to estimate is some sort of M which is actually a subset of domain of attraction. So, in other words, domain of attraction can be larger, but you will be able to conclude only a subset of that basically. Okay. So, the Lassalle's I mean proof part of it is rather easy. You can in Lassalle's theorem you can simply take E equal to that and then the result will follow actually. Okay, we will continue with that example. So, example what you are discussing, V and V dot happens to be like that, and V dot happens to be less than 0 as long as this condition is satisfied. Now, let us examine a little bit further. Take V of x like that and V dot is already like that, and we already know that happened. So, what we do here is let us consider x 1 is equal to 1.6, okay, and x 1 is equal to minus 1.6 also later. So, what you are telling here is we are examining this situation on the boundary line, what will happen we will let us examine and all that. So, on the boundary line it happens to be like x 1 is equal to 1.6, that means it is a function of only x 2 now. x1 is already evaluated at 1.6. So, the v happens to be a function of only x2 on the boundary. So, what happens on the boundary, whether there is a local minimum maximum or not, let us try to analyze actually. So, if you take first order partial derivative, this for analyzing local minimum maximum, that needs to be equal to 0, and hence x2 if you evaluate that happens to be minus 0.8 actually. So, and similarly if you take the other one, x1 is minus 1.6, it is again if you do the same algebra, it turns out that it is plus 0.8 actually. And it also turns out that del x2, sorry, see this is this can happen both for both minimum and maximum. So, we want to make sure what is really happening, and for that we need to have partial second order derivative sort of thing. But anywhere if you take a second order derivative, then whether it is plus 1.6 or minus 1.6, it happens to be plus 12, which is greater than 0, because it is plus 12 only. Here is plus 12x and there it is also plus 12x, the constant will go. So, it turns out that at both these points your double derivative is positive, and hence you have got a local minimum actually. Okay. So, that the thing that we discussed before, that there is a stripe sort of thing and all that, okay, this stripe, okay, x1 x2, okay. This is x1, this is x2, this is 1.6, minus 1.6, this stripe that we are talking. Now, we are having some x2 values also, and if it x1 is plus 1.6, x2 happens to be minus 1.6, minus 0.8 actually. So, that means we are talking about a point here, and we are also talking about a point here. Okay. So, these 2 points happens to be local minimum actually. Okay. So, then the solution can get trapped there, it will never go to origin actually after that. Okay. If it happens, if it is trapped actually, it will never go to origin after that actually. Okay. Anyway, so what it tells us is because this v of x has local minimum on the way and all. So, let me try to ignore this, okay, let me try to exclude those points and all that, and then I will define some sort of a set which will avoid that actually. Okay, it will not go towards the local I mean that minimum thing. So, then I will evaluate this Lyapunov function, both of the Lyapunov function at both the points happens to be like that. So, I will simply try to avoid from there actually. Okay. So, in other words, if I define a set for which this M is a subset of D, for which the v of x happens to be just a little bit less than this point, this value, whatever value is there, there is just a little bit less than that, minus epsilon is a small positive quantity, then it turns out that local minimum values are local minimum points are excluded from this set, and once that is excluded, x of t has no other go but to go to 0 actually. Okay. So, that means if I define a set properly like that, then it turns out that that is an estimate of my domain of attraction really. Okay. So, I mean that is all about this conservative results and things like that actually. Okay. So, before we stop this lecture, there is another interesting result, sometimes it is useful. So, let us study that very quickly, and it tells you that if my v dot happens to satisfy some v any function of time, and if it satisfies this inequality, then for all time this inequality is also satisfied. Why is that? Because if I define this z of t as something like v dot plus alpha v, and then consider that as a linear differential equation, remember z of t is less than 0 by construction, this inequality is there. Then if it is a linear system equation, I can solve it, I mean like a linear system equation, then it turns out that this integral thing, okay, is in this is less than equal to 0, and this is always greater than equal to 0, this is a positive integral sort of thing. So, the entire thing will be less than equal to 0, and hence this v of t will be always less than equal to 0. So, if I somehow if you can show that this inequality is satisfied, then v of t will ultimately go to 0, and that is the point actually. Anyway, so that is the interesting thing I thought I will share with you, but all other things are important. These references are already there, we discussed about that. Many of the things I have taken from first and second primarily, you can see some of these references for Lyapunov theory. Further classes we will see the utilities of this Lyapunov theory in different contexts actually. Alright, let me stop here. Thank you.